Hello. We are moving on today to our very last set of notes for this unit. So today we're going to go over this idea of independence, about how certain things certain events can be completely independent from one another. We're also going to have a little like bonus practice at the end. So notice that you don't have a lot of stuff on that back page. We're going to add one more practice problem because from what I've heard from you guys, practicing Venn diagrams is where you're feeling very nervous. So we're going to do a Venn diagram practice problem as well at the very end of these notes to try and get you confident, and then we'll do that in class together. Okay, so independence. The idea of independence is that these two events that are happening have no sway or no like overlap with each other, right? They don't have anything that could be um, interfering with the other event, as well as they don't have anything that have anything to do with each other. They don't have any type of answers that might be the same between the two. They don't share a same number between both of them. They're completely independent. There's ways that you can mathematically prove that something is independent. So on a test, when you're asked, like, are these events independent? What they're asking you to do is to use ways for independence, use ways to mathematically prove that they are independent. And there's two different ways that you can prove it. The first one is that if the probability of A intersection B, so this is the bridge, right? So this is the bridge that connects the two, so the things that they share. So if the things that they share are equal to just the multiplication of those two events, which is pretty much what we've been doing. What's the probability of this and this, right? And then we multiply those two things together. Then the events are independent. It can also go the other way. If the events are independent, then the probability of the intersection of these two events results in the multiplication of them. So that's pretty much how we've been using this first line here, this first sentence, this first theorem that we have, is that we've been using it backwards. Is that we've known, maybe you've been aware of, or maybe just it's kind of in the back of your mind, that these events are independent. They don't have anything to do with each other, so you just get to multiply them and don't have to worry about it at all. Okay, the next way that we can prove it is that if the probability of A given B is just equal to the probability of A, then the events are independent. So it's this idea of the probability of A given B, which is the probability of A and B divided by the probability of B. It's this idea that the probability of A and B, it kind of follows suit here, that if they're independent, then it would be A times B, right? So if they're independent, the given formula says, hey, that's just A times B. And then if you divide B out, that guy would cancel, and you're left with just the probability of A. So kind of these two sentences go together, and they're both true if the events are independent. And so if you're asked to prove that they're independent, you might go in and calculate it and say, like, hey, look, the numbers are the same, and therefore they must be independent. We'll practice it. In many countries, the police stop drivers on suspicion of drunk driving. The stopped drivers are given a breath test or a blood test or both. In a country where this problem is vigorously dealt with, the police records show the following. 81% of the drivers stopped are given a breath test, 40% a blood test, and 25% both tests. So let's talk for a second about how we can visually represent probabilities. We've done a lot so far with representing probabilities as tree diagrams. And tree diagrams are great when we have a sequential event sequence happening. So first we're going to take the bus, and then we're going to talk about whether or not we have coffee. First, we're going to pull out a marble from the bag, and then we're going to pull out another marble from the bag. It's this idea of one event, then the next, right? And so that is a really great situation in which you would want to use a tree diagram to have this idea of paths that you can follow. First step, second step, third step, even. Other types of probabilities are this idea of like this general world of a situation that could happen. So we've done it in class a little bit with creating Venn diagrams, where we've had like the two Venn diagrams, and then we talked about like the universe that surrounds the Venn diagram. and which is that rectangle that's on the outside of the Venn diagram, and it's representing like all of the things that could possibly happen. And then what's the probability of picking this thing out, or what's the probability of having both of these things together? And that's when we use a Venn diagram. And so see here that this isn't necessarily like first they're given a breath test and then a blood test, right? There's not like this idea of a sequential amount of events. It's just this like generic probability. When we have this generic probability, is a good idea to start making stuff into a Venn diagram. It won't always tell you to make a Venn diagram, which is tricky. So try and keep that in mind. If it's the idea of like a sequential amount of events happening, tree diagram. But if it's just this like generic probability, you're probably making a Venn diagram. And if you don't know where to start in a problem of probability, it's probably because you need to look at it in a visual way, which means you need to create some sort of diagram in order to figure out what's really going on here and what information do you actually have. And so then this is where the big puzzle aspect comes in, right? So we've got 81% of drivers that are stopped by a blood test and given a breath test, 40% a blood test, and 25% both tests. So we've got this situation of breath versus blood tests. And then it's surrounded by this box, which we label U. U stands for the set of all possible outcomes, right? Or the universe, as Raphael so poetically put it in our class the other day. So the universe is this idea of like anything else that's on the outside of the Venn diagram. It's all of the other options that haven't been represented inside of here. So we have this information, and it's a riddle. Where do these pieces of information go? What do they mean visually? So if 81% of the drivers stopped are given a breath test, that means that this whole circle right here represents 81%. In other words, a probability of 0.81. 40% are given a blood test. So this whole circle is 40%, or a probability of 0.4. Okay. Now, the thing is that when we know what's going on with a whole circle, that's helpful information for a later part, right? That's helpful information to say, okay, well, I know that this whole bubble is 0.81, but I don't know what the part inside of that bubble is. And then that's where this last piece of information is really helpful. 25% are given both tests. That is the most useful piece of information here because it's a very specific one spot. 25% both tests, that means in here, this part where they overlap, right, is 25% of the data and has a probability of 0.25. So if I put that piece of information in here first, 0.25, it starts to open up this like domino effect of how I can fill in the rest of the Venn diagram. Because then I can go back to the blood test. If this whole bubble is 0.4, right, and part of that bubble is now 0.25, I've taken up 0.25 of that 0.4 probability, right? I've taken out 25% of my total 40% of blood, yeah? So that means that the other 40% of the people who were tested is the rest of the 40% is 25 minus 40, which is 15, right? So then this is 0.15 or 15%, okay? So let's recap that. We knew that this was 0.25 because this is for both of the tests. And so that's the most specific part of our Venn diagram. So we fill out our most specific part first, if we can. And then we say, okay, well, then the whole bubble has to be 0.4 because it says here that that whole bubble needs to be 0.4. Well, I've just put 0.25 in here, so the remainder has to be the subtraction, which is 0.15. Because when I add these two together, they add up to 0.4 or 40%. I can then also move over to the breath test. This whole bubble right here is supposed to be 0.81 or 81%, but I'm using up 25% of that 81%. So to know what's in the rest of the breath test probability, I just need to subtract the 2, and that ends up being 0.56. So that's 0.81 minus 0.25. Okay, so that's the puzzle aspect where like, okay, we find out the piece of information that's the key, the thing that's going to unlock all the rest of the information, right? This is helpful information, but we need a key in order to access that information. And it just so happened to be this one. It won't always be the same. Sometimes your key is going to look different. And this is the puzzle aspect of like, okay, which of these pieces here visually help me be able to figure out this puzzle and open up the doors to lead to the rest of the probabilities. We're not done yet. You always have to double check. We need to represent 100% in here. In other words, all of the numbers that we write in this situation need to add up to 1. And right now, they don't. 0.56 plus 0.25 plus 0.15 is what? By adding all of those together, you would have gotten 0.96, which means we have not represented 0.04 of the data that happened. So that means that 0.04 of the people who were pulled over, who were stopped, were not given any test. No breath test, no blood test. Okay? So then that means that out here in the sample space, neither test is 0.04. And that's how we build our Venn diagrams, this idea of a puzzle. What's the most helpful piece of information and how can I use that to unlock the rest of the information? All right. So then moving on to the actual questions, we haven't even gotten to any of the questions. This is just information, right? And when I first grabbed this problem, they didn't give you space to build a Venn diagram. I put the space in there to build a Venn diagram. So they won't always be very clear that you need to build a Venn diagram. So try and remember this idea of like a sequential amount of events would go into tree diagram versus a Venn diagram, which would be a little bit more just a generic, like this had a probability of this or a probability of this or a probability of both. If you see anything about both or neither or something like that, it's probably a Venn diagram situation. And if it says what's the probability that the driver is given a test and you're looking at this information, you're like, how do I know how to do that? It probably means that you need to be building a Venn diagram. Because now that we have a Venn diagram built, it's easy to see. What's the probability that a suspected driver is given a test? Well, that's here or here or here. So that would be 0.56 plus 0.25 plus 0.15, which we've already calculated is 0.96. The probability is 0.96, or in other words, 96% of the drivers were given a test.